Hi friends, we are going to be working through our Worksheet 6 tutorial, which is Worksheet 6, and we're just going to start with number 3 to kind of help you with these, we call these flatwood problems. So these are problems where you have a block on a table and a block off the table. It's very, very similar to the problems where we have a pulley and there are two masses. So it is very similar. You'll see how in just a moment. Okay, so first things first, I need to draw my FBDs. So I'm going to draw my box A FBD here, and I'll draw my box B FBD a little bit lower just so I can keep it straight. Box A will have a force of gravity on A, a normal force from the table. And these are going to be equal and opposite because we don't have any other forces that are acting on the block in the vertical direction. There is going to be a force of tension that is to the right. And there will be a force of friction as well, because we have the coefficient of kinetic friction. So there is a force of friction that will oppose the motion of block A. Okay, then for B, I'm going to have my force of gravity on B and a force of tension that is up on B. And because these two forces of tension, this is the same string as this string, these are going to be equivalent. So this force of tension will be equal to this force of tension, and this force of gravity should be a whole lot bigger than that force of tension. So I'm just going to make it super obvious. Okay, so that's my first step always, is to write my FNet equation, or draw my FBDs, identify anything that is the same, and then, so I identified FG and FN for A, and FT for A and B as the same. So then I'm going to need to look at my axis of rotation, or my axis of acceleration, to make sure that I know what is positive and what is negative. So system A, so this block, is going to accelerate like this, right? So B will accelerate downwards, A will accelerate to the right. So this is our axis of acceleration, which basically means that any force that goes to the right with A is going to be positive. Any force that goes to the left on A is negative. For B, any force that goes down is going to be positive, and any force that goes up is negative, because that would be opposite of the negative direction for these two masses is going to be the direction opposite of acceleration. So it's opposite of the direction that that object is going to accelerate is the negative direction. So that means when I look at these forces, force of friction, negative, force of tension, positive, force of tension, negative, force of gravity, positive. So when I go to write my FNet equation, and this time I'm going to write my FNet equation for my system, which is different. My system FNet, first of all, will be the sum of the two masses. So it'll be MA plus MB times that acceleration of my system. And the forces that are causing that FNet would be FGB minus FTB. And then if I combine those with the forces that are accelerating object A, that would be FTA, a positive FTA, minus our force of friction on A. So again, just to kind of review how I got that, was I'm looking at the forces that are causing the acceleration. So it's kind of weird because I'm adding these forces that are horizontal to forces that are vertical. But reminder, for object A, the horizontal forces are the forces that are with that axis of acceleration. And the forces on object B that are causing that acceleration are vertical. So those forces together are going to combine to make a net force. So looking at this, these two forces are the same in magnitude. So they're going to cancel out. And what I'm left with is MA plus MB times A, common mistake, times A is equal to FGB minus the force of friction on A. Okay, so then we've got a bunch of questions. I will have you answer B and you answer C in your groups tomorrow when we get to class. But we are going to calculate some of these things for when the block actually starts to move. So for D, E, and F, we're looking first for the acceleration of the block. Then we're going to look for the coefficient of friction to make the block remain motionless. And then we are going to calculate the force of tension. So I'm trying to solve for the acceleration. And with these two body systems, I should look for things that are the same that I can use substitution for. So like substitution in like algebra. So Ft is the same. And so I've actually already eliminated Ft from my equation. So at this point, I just need to solve for these values to be able to get this acceleration. So let's look at what I'm given. I am given a 10 Newton hanging mass, a 40 Newton block on a table, and the coefficient of friction. Do I have the mass? So let's start there, right? Because I'm given this is the equation that I'm going to be using. Do I have the mass? I don't. I have something measured in newtons, which is the weight. I do not have the mass. So the first thing that I'm going to do is I'm actually going to solve for the mass. And we'll solve for mass of A, the block on the table. So we've got Fg equals mg, right? Because that's how we relate weight and mass. The weight of A is 40 newtons. G is the gravitational field strength, which is 9.8 on Earth. And so our mass will end up being, real quick, I'll plug that in, 4.08. Then I'm going to solve for mass B. And use the same equation, except with 10 newtons this time. And that mass will be 10 divided by 9.8, which is 1.02 kilograms. So at least now I have these two that I can plug in to my equation over here. So that's brought me 2 of the variables, but I need to identify what FGB is, and I need to identify what the force of friction is to be able to solve for acceleration. So how can I find or calculate FGB? Oh wait, I was given FGB because look, I was given the force of gravity, the weight of B. So I actually do know this. This was given to me in the prompt. What was not given to me was this force of friction. So I'm going to need to solve for the force of friction. So I'm going to start with my force of friction equation, which is on my AP Physics 1 equation sheet. And it's written like this, less than, but we know with kinetic friction that it's not actually less than, it's equal to, and this is our coefficient of kinetic friction. So the coefficient we are given as 0.2 in the problem, so it's given as 0.2. And I'm going to need the normal force to get the force of friction. And this is the force of friction on A. So if I'm looking for the force of friction on A, this normal force needs to be the normal force on A. So I'm going to look at my FBD for A. Oh, and the normal force on A is equal to the weight of A. So I'm going to use that 40 newtons, that's the weight of A, and plug that in instead. So because the normal force on A is equal to the force of gravity on A, because it's not accelerating, this is from my FBD, I can just replace it. And that simplifies to 8 newtons. So now I can plug this value in to my equation up here. And I have all those variables except for A, which is what I want. So mass of A is 4.08 kilograms. Mass of B is 1.02 kilograms. Force of gravity of B is, 10 newtons. Force of friction on A is 8 newtons. And then I can solve for this problem. 4.08 plus 1.02 would be 5.1 kilograms. 10 minus 8 will be 2. Then if I take both sides, I divide by 5.1. So I do 2 divided by 5.1. I get 0.39 meters per second squared. So this will be my answer for part D. Okay, so for the minimum value of coefficient of static friction, in order for the block to remain motionless, what that would mean is that our system would need to be completely at rest. So what that would mean is that my FBD for A would have balanced forces. So that would mean FT would be equal to the force of friction. And that would also mean for B that FG on B would need to be equal to the force of tension. And if I use some deductive reasoning, right, Ft and Ft are already equal. So basically, if Ft on A is equal to the force of friction on A, and Ft on B is equal to the force of gravity on B, that would mean that the force of gravity on B would need to be equal to the force of friction on A. And I can take that and say, okay, 10 newtons is my force of gravity on B. And my force of friction equation is mu S times Fn of A. There we go. And I can plug in my normal force on A. That's the same because my force of gravity on A hasn't changed. And that would mean that my coefficient of static friction would have to be at least, divide both sides by 40, 10 divided by 40 is 0.4. Wait. Yeah, 0.4. No, 0.25. 1/4. 0.25. So that would be the minimum value of our static friction. And again, that came from drawing FBDs. I had to draw an FBD again to be able to answer that question. All right, now for part F, I'm supposed to calculate the force of tension. And for part F, what I'm going to do is I'm going to look at just one of these objects. I'm going to look at, if I'm calculating the force of tension, I can't look at the system of the two. I have to look at one individually. So I'm going to look at B. So F net on B would be MB times A, which would be FGB minus FT. So basically, I need to make sure that I have FGB, which I do. I do have FGB. That's the 10 newtons that's given to me. I need to have MB, which I actually solved for before. It's 1.02 kilograms. And I also need the acceleration, which I solved for in part D. So I'm going to plug in that 0.39. So 1.02 times 0.39 equals 10 minus FT. So again, I can solve that problem and get to that acceleration. Or get to the force of tension, so, excuse me, not the acceleration. The reason why the acceleration of A is the same as the acceleration of the system, is the same as acceleration of B, is because you can imagine those different spots on the string as the system accelerates and moves. And that string, parts of that string can't be moving at different accelerations, or else we would see slacking in that string. We wouldn't see that uniform force of tension throughout a string that we always see. Okay, last thing I want to talk about is problems like this. So when you have a system that you're pushing A directly, so this is the force from the hand on A. Is the hand pushing B? Is the hand in contact with B, as another way of saying that? No, the hand is not in contact with B. So what that means is that the force on B that is this direction is not from the hand, but it's from A. So this is where your on-by notation becomes really important. And that means if A is pushing B, because of Newton's third law, we know that B is also pushing A. What direction is B going to push A? Or sorry, on B by A. Or on A by B, and then by A on B. Right? We've got that reverse on by notation, and that means those forces are equal and opposite. So that's just a start to the FBDs. These FBDs are not complete, but this is a way for you to start these FBDs because we haven't done a problem like this before. Okay, so your homework is to do the rest of this FBD for number 4. You're going to do your FBDs and F-net equations for number 2 and for number 1. Good luck. Let me know if you have any questions.